Hello everyone and welcome. In this video we're going to be introducing the common types of relationships in differential equations. In the first part we talked about how to solve any differential equation, but right now we're talking about paragraph questions or the passages that come to you in your exams that are basically going to be having some type of pattern that you need to identify in order to solve them correctly. So let's get started with the first type of relationship, which is the rate the rate at which x is increasing or decreasing. X is increasing or decreasing is constant. So what that means is that, now we know the rate itself means dx on dt. The rate of change in x is just the change in x per unit time. So it's dx on dt. So it's increasing or decreasing means that's basically that the derivative is going to be either positive or negative. And since they said it's a constant, that means that we're going to be translating this sentence exactly word for word. So first off, we say rate is dx on dt, and then increasing or decreasing, that's going to be positive or negative, and constant means we're just going to place a constant there. Now, from here, we're able to find the general solution to this, such that we know the relationship between y and x, the initial and the general solution for, the initial and the general relationship between x and y, without finding the k or the initial constant. So let's see how we can solve this. Generally, you're just going to be sending the t dt to the other side, separating, then you're going to be integrating, and then obviously you're going to put in a constant. So this would have been the initial relationship between, x and t, not x and y. And so this is the initial solution. Okay, now in a passage he will give you multiple points, like initial conditions, like 0, 1, these different kinds of points, which are going to help you find the k and help you find the c. Depending on the number of constants that you have in a differential equation, you're going to have a different number of points given to you. So let's start with this example. You can see it's pretty long, but just reading through it, everything is going to be simplified. So let's start with water flows out a tank through a pipe at the bottom, and at time t seconds, the depth of the water is x meters. So we can clearly identify here that the relationship is between x and t, where x is the depth and t is the time. Now at time t equals 0, the depth of the water is 3 meters. So here we're given an initial condition of 0, 3. We write this down as a point. After 50 seconds, the depth of the water is 2 meters, and so you can see here that the depth of the water is decreasing. Okay, so let's just write again another point. So it's 52. It's going to help us find another constant. The more points, the more constants you're going to have to find. Now, given that the rate of flow is constant, he already gave it to us. There you go, jackpot, right? So this is the condition that we were looking for, the relationship that we were looking for, the rate of flow being constant. And we know the rate of flow is dx on dt. For it to be constant, it means for it to be equal to k. And since he said producing a constant decrease, that means that the k has to be negative. There has to be a negative in front of the k. And find the time at which the depth of the water is 1/2 meters. So he gave us the depth of 1/2 meters, but the time is unknown, and this is what we are looking for in this question. So in order to find the time, I know since I'm given a differential equation, I'm going to first have to solve it, and then obviously plug in this depth to find the time and solve for t. So let's go ahead and first start by solving the differential equation like always. As I have mentioned, to solve this, to obtain a general solution, send t to the other side, integrate either side, you get x equals to negative kt plus c. Given this initial condition, you're able to find the c, since x equals to 3 and time equals to 0, which cancels out the k, and so c is equal to 3. Let's look at this point over here. We're able to find the k using it. So since x is equal to now negative kt plus 3, if I plug in this point, which says 2 equals to negative k times 50 plus 3, I'm able to solve this to obtain negative 1 equals to negative k into 50, which means k is equal to 1 over 50. And please don't be surprised when you find such numbers when you're solving, because you're going to find even smaller and weirder numbers when solving, and we're going to see a bunch of examples. But let's continue now. We've talked about how the equation, I'm going to continue right here on the side. The equation now is equal to x equals to negative 1 over 50 t plus 3. And he wants the time at which the depth is 1/2. Sorry for the m over here. There's no need for units. 1/2 equals to 1 over 50 time plus 3. Solving this, we can send 3 to the other side, which gives us negative 5 over 2 equals to negative 1 over 50 t. If you multiply by negative 50 on either side, you should get time equals to 125 seconds. And here you go. We've solved this question. Okay, let's move on to the second relationship. So the second relationship is that the rate at which x is increasing is proportional to x. I know it sounds weird that the rate at which x is increasing is proportional to x, but what this means, translating it, is basically saying that the rate at which x, when we know that's dx on dt, is proportional to x, just like we have talked about before. Proportionality means we're going to have a constant in there, and that's going to be, related to it's going to be the constant of proportionality. So we're going to say that it's kx. Since they are proportional to one another, we plug in a k, we place next to it an x. This means that they're proportional. Now, this is because it says increasing, this is going to be positive. But if it were decreasing, we're going to place here a negative sign. Okay, so dx on dt equals to k times x. Now, to find a general solution to this, it's pretty simple. Just send that dt to the other side, and then integrate either side. Obviously, you can't integrate with respect to t when you have x here, so you're going to have to divide by x on either side, which gives us 1 over x dx being equal to k times dt, which then we can integrate either side, and we get ln of x being equal to kt plus c. This is a general solution. Another way of writing down our general solution can be by making it exponential instead of logarithmic. So we can say that x is equal to e to the power of kt plus c. And when we have addition in powers, that means that it used to come from multiplication. So x is equal to a into kt times e to the power c. And we know that e is a constant and the power c is a constant. So this entire thing can be replaced by one constant. So we can remove this entire thing and place here a for another constant. This is not necessary, but if he were to ask you to show that this relationship where there is proportionality looks a certain way, all you have to do is just to simply go and say that e to the power c or e to the power whatever number it is going to be the constant, which happens to be a. And if you want a shortcut, remember that a happens to be the initial condition of x. So at time t equals 0, let's say, if he gave us a x equals to 5, a will be that 5. So that's what I wanted to say. Now let's go ahead and get started with our first example. Okay, example number 2 is even longer, but that doesn't matter. It's just my handwriting is huge, so let's start by reading. In a certain pond, the rate of increase of the number of fish is proportional to the number of fish itself. So we've talked about this example again. This is the second relationship that we've talked about, proportionality. And in this case, we said that the rate of, because I said the number of fish is n, we're going to say that the rate of increase of n, which is dn on dt, is equal to, because they're proportional, that means it's a constant, and since it's increased, so it's positive, kn. He says that present at time t. Now, assuming that n can be regarded as a continuous variable, write down a differential equation relating n and t together, and hence we already have written that down, and hence show that n equals to a times e to the power of kt. Now, to do this, it's pretty simple. You just need to solve in order to make n not dn or dt over here. So first things first, send the dt to the other side, separate by dividing on n, and so by n we're going to get 1 over n dn being equal to k dt. You integrate, you get ln of n being equal to kt plus c. Notice it's a logarithmic one. He wants to be exponential. To change that, you just make it exponential right here, and because we know that this over here came from multiplication, we get n being equal to e to the power kt times e to the power c, and this over here can be regarded as a whole other constant like a, which he has written here. So n equals to a times e to the power of kt. Very weird shape, sorry about that. Okay, now let's talk about what he has said after. Now, in a revised model, it's assumed that the fish are removed from the pond by anglers and by natural wastage at a constant rate of p per unit time, so that the dn on dt is no longer equal to just k times n, it's equal to kn minus p. So notice that when we are removing something at a different rate, the overall rate of increase or change of something, like the change in number of fish, dn on dt, is actually going to be the subtraction of the two rates, the rate of increase subtracted from the rate of decrease or the rate of removal of the fish. So it's minus p. you're going to be asked to do like other questions where basically you're going to have the subtraction of the rates lots of different times. So don't worry about it. Now, given that k equals 2, p equals 100, so we're going to write this down over here. If k equals to 2, that's the value of the constant. Okay, so k equals 2, p equals to 100. So, and initially there were 500 fish in the pond. So obviously that at time t equals 0, there were 500 fish in the pond, because it said initially. And so there were 500 fish in the pond. Solve this differential equation expressing n in terms of p, and give a reason why this revised model is not satisfactory for large values of t. Well, let's go ahead and do this. First things first, we need to express n in terms of p. Well, we know that p is a constant rate, which he said was 100, right? So I don't think it's p. I think it's supposed to be t. Yeah, sorry, this is a spelling mistake. Okay, so let's write this down. T. Okay, yeah. So in order to solve this over here, we're just going to write down this differential equation and integrate it just fine. So let me just take another page for this. Okay, so dn on dt must equal to kn minus p, where k and n and p are given to you. So that's 2n minus 100. If you want to integrate this, you're going to go and say that we're going to send the dt to the other side, which now we're not used to this. We're just used to dividing by n. But now if we divide by n, we're going to get 100 over n, which is not useful. So I'm going to divide by the whole entire thing, giving me this fraction. Now I'm going to get 1 over 2n minus 100 being equal to 1 over, I think it's just 1, I believe, yeah. So it's just 1 dt. Now this is dn. We can integrate either side now, and we're going to say it's ln of 2n minus 100 and divide by the derivative of what's inside, t plus c. Now he wanted it to be just in terms of t, so we're not going to be using this constant anytime soon. And given this initial condition, which was 0, 500, we're able to figure out what the c is. So ln of 2 times 500 minus 100 divided by 2 must equal to t plus c, which is just like saying ln of 900 over 2 is equal to t plus, is equal to t is equal to 0, I believe. So it's just c being equal to ln of 900 over 2. Now let's go ahead and see what he wanted. Give reason why. So first off, I want to express n in terms of t. So obviously don't appreciate having n inside here when he wants n as a subject. So we're going to make n the subject now. Ln of 2n minus 100 divided by 2 must equal to t plus ln of 900 over 2. So we're going to make it an exponential function, which gives me, okay, 900 to the power of half e, which is equal to, first I'm going to be multiplying everything on this side by 2. So this cancels this 2, and so I get now to obviously cancel this and say that 2n minus 100 is equal to the exponential to the power of 2t plus ln of 900. And we know when we have a ln up we can cancel it with the e, and so just go send it down, so that it's 2n minus 100 being equal to 900 e to the power of 2t, which we can then send the 100 to the other side. So we're going to add 100 and add 100, and this cancels, and we can divide everything here by 2 to get us n being equal to 900 e to the power of 2t plus 100 and the whole thing over 2. Now then he talked about how why this revised model is not satisfactory for large periods of time. So again, I'm going to show you what he said. So he said, give reason why this revised model is not satisfactory for large periods of time, or large values of t. Large values of t means infinite time. Okay, this is what he means when he says large. He means infinity, at least approaching infinity. So instead of t, how about we substitute in infinity? Right, so anything to the power of infinity is actually infinity, unless it's so anything to the power of infinity is infinity, meaning this whole thing is infinity. And anything times infinity is also like a bigger infinity. This is like a 900 times infinity. And then plus 100, and then divide by 2, we're talking about infinite number of fish, right? So this is going to be an infinite number of fish, which I'm not sure this tank is going to be able to hold an infinite number of fish. You are literally you're moving the fish such that you're able to fit in more fish, but then you have the fish they just keep on increasing. They don't really care for the subtraction of like, the other fish. So you're gonna get an infinite number of fish by like huge periods of time. So this is obviously not satisfactory. This model needs to be revised even more. Okay, let's talk about the third and last relationship. We have the rate of increase of x is proportional to 1 over x, or in other words, it's inversely proportional to x. Okay? So notice when he says inversely proportional, he means that it's proportional to 1 over x. What this means is just you're going to say that dx on dt is equal to, obviously, a constant of proportionality times 1 over x. In other words, like, this is just, this over here being like proportional to 1 over x is just the same as saying inversely proportional. So if we did not tell you that it's proportional to 1 over x, do not panic. Just remember, I'm going to put a constant, I'm going to be dividing by x. This is what it means to be inversely proportional. Okay, you're going to have x in the denominator. Okay, so I don't like to express it this way. I just like to say that directly dx on dt is equal to k over x for inversely proportional or proportional to 1 over x. To find a general solution for this guy over here, we send everything to one side. So send the dt to the other side, multiply by x on either side so that you can cancel it from here, and then you can integrate either side, and you're gonna get x squared over 2 being equal to kt plus c, which then becomes x squared being equal to 2kt plus obviously 2c, which can be replaced by a whole other constant like, for example, a. Okay, you can keep it this way if you just want the relation, but if you want x in terms of k, you can take the square root and put a positive or negative. Wow, I like the square root. Okay, 2kt plus a. So this is the relationship, or let's say x in terms of t. Now let's go ahead and do an example on this. Okay, let's look at example number 3. A circular oil patch on the surface of water has a radius of r meters at time t minutes. So we're gonna see a relationship, I believe, of r with t. When time equals 0, r equals 1. Let's write this down as a initial condition. At time t equals 0, the radius equals to 1, and at time t equals 10, radius is equal to 2. It says it is desired to predict the value of t, or capital T, when the radius is equal to 4. So it's unknown here, or t, when radius is equal to 4. Okay, because in a simple model, the rate of increase of r is taken to be a constant, so find t for the simple model. This is example number 1, or relationship number 1, which we talked about when we said that dr on dt, or the rate of change of something, is a constant, and since it's increased, so it's a positive constant. Okay, and given this, in order to find t, we're going to first need to find that initial, general solution, in order to plug in the r to find or solve for t. So to do this, it's pretty simple. We just go k into dt, and then we can integrate the either side, and we get r equals to kt plus c. To find these two constants, we just need initial points or initial conditions like this in this case. So we start with the first one. 1 equals to 0 into time plus c. T cancels, and the constant will equal to 1. And then the second condition is going to be 10 and 2, which means that the radius is equal to 2 when time is equal to 10 minutes, and we know the c now is equal to 1, which means that k is equal to 1 over 10. So here we have our two constants in this case. Now, given we have the constants, are we able to find the t? Yes, we are. So we're going to simply say that radius equals to 4k, which is 1 over 10 now, times t plus 1. So that gives us 3 on the other side being equal to 1 over 10t, which means that time is equal to 30 minutes. Okay, let's start with double I. Now in double I, he says in a more refined model. So we've changed the model, we've changed the rate of change. Okay, the rate of increase of r is taken to be proportional to 1 over r. When we've talked about this just now, we said to be proportional to 1 over r is to be inversely proportional to r, which means that dr on dt is equal to k over r. Express this statement as a differential equation. Find the solution, find t for this model. So let's first express this as a differential equation. It's pretty simple. Let's go ahead and do this. So for double I, I'm using this pink color. So we're going to say for double I, dr on dt is equal to k over r. And since it's increased, then it's positive. If it was decreased, I'd say it's negative. Let's continue. He said express this statement as a differential equation. We already did this. Now find the general solution. To do that, I've told you to just send the dt on this side, so k over r dt, multiply by either I or either side, we get r dr equals to k dt. If we integrate, we're going to get r squared over 2 being equal to kt plus c. Now this is the general solution, but before this I'm going to be multiplying everything by 2 because I don't appreciate r having, being multiplied by other things. And so we can just erase this and write it as a different constant. Let's call it a. Now, what's it called? Find the general solution, find t for this model. To find t, and first off, I'm going to be using these initial conditions because they were here. They don't just have to do with I, they have to do with the entire question. Therefore, all the points which are right here are also used in this question. 0, 1, 10, 2, and t at radius equals to 4. So let's go ahead and find our a, find our k, and then find the t. So to find a, I'm going to be plugging in this point, which I've told you, it's 1 being equal to 2 times 0 for t, which basically cancels out the k and gives us a being equal to 1. To find k, we're going to be able to plug in the second point now. So let's say that it's going to be 2 squared, which is 4, be equal to 2k into time of 10 plus 1, which means that 4 minus 1, that's going to be 3, which equals to 20k, and therefore k in this case is equal to 3 on 20. Now to find the time, it's pretty simple. Just go ahead and plug in 4 squared for r, and then 2 into 3 over 20 times time plus a, which is 1. So we know that here we're going to get 3 over 10, and then we can send 1 to the other side, which is going to give us 15. So 3 over 10 t here is going to be capital T, and the capital T in this case is going to equal to 50 minutes. Okay, and this over here is your solution to this question. I hope this video was useful. Thank you for watching.